do it. Another question here, the circuit diagram shows a simplified version of a heating circuit. In a hairdryer, the switch can be either turned on or turned off. Just open at the moment. Select and use equation from page 2 to answer the following questions. Calculate the current supplied. So I need current, I've got voltage, I've got resistance. So I need to use this equation again, VIR. Okay, that's the only one that satisfies all the values. So just put in the 230 over 40 gives me 5.75 amps. 3 marks. 3 marks for that. God, if you're losing 3 marks on that, then you need to watch this video over again. Calculate the power produced by the resistor when S1 is open. So I've got a power now. P equals, what do I know? Well, I know my current now is 5.75. I know my voltage is always going to be the same, to be 230. There's an equation I can use. There is PVI, PIV, P-I-V. If I'm putting that into a triangle, P is going to go on top because V is already with I, but I don't need to because it's just V times I, or I times V in this case. Oh, another 3 marks, look. 5.7, 5 times 230 is going to give me 1322.5 watts, and you don't even have to change anything there. It's all there for you. 6 marks, just waiting. Gets a little bit trickier. The company who make the hairdryer state that the amount of heat energy produced each second will double when the switch is closed. Discuss if this claim is correct. So they're saying if that switch is closed, then you're going to get more energy. You're going to get double the energy for the same volt. Well, if switch 1 is closed, another 40 ohms is added. And what do we know about in a parallel circuit? It decreases. That's going to half. It is. I already know that. I'm going to show the calculation anyway. So switch 1 S is closed. Another 40 ohms is introduced to the circuit. It's in parallel. So we're going to reduce the total resistance. It's going to go down. And if resistance goes down, then current goes up. And if this halves, then current's going to double. And that's what they're saying. So here's my calculations. If switch 1 is open, then the resistance is just 40 ohms, okay? If this is open, there's your power supply. They've stuck it on the bottom for some reason. It's usually on top. But it's exactly the same circuit. Current's going around. There's it going. And it's got 40 ohms resistance. Now they're going to close this one. So the current now can split. Okay? And this is going to half. I'm going to show you how it halves now, because you've got 40 ohms here, 40 ohms here. I can use 1 over R equals 1 over RT, 1 plus 1 over R2 to show you. So if I've got 2 resistors of 40, so 1 over 40 plus 1 over 40 gives me 0.05. Well, let's calculate the overall resistance now of the circuit. Okay. Let's get the reciprocal of that. I don't know what I was on about there. So R equals 1 over 0.05, because I've needed to do that because 1 over RT now equals 0.05 from this long calculation. So what's R on its own? I need to flip it, take the reciprocal. So R equals 1 over 0.05, and that's going to give me 20 ohms. So by having this switch closed, it's going to give me 20 ohms instead of 40 ohms. So it actually halves the energy. Halves the resistance, which doubles the energy. So I've said there, the claim is correct. The resistance is half. Brilliant. And then let's shrink these. So this is going to have to be 2 videos here. In a practical lesson, a group of pupils investigate the voltage. So a lamp and a resistor. The currents and voltage shown there. And did we have to plot it? No. Oh, only one we needed to plot. We need to plot the resistor, which is that nice straight line there. Be careful with your scale here. I think this is because it's worth 2 marks. But look at this scale. It's like, who on earth does that? 0.25. So every small box now, because there's 10 boxes in each big square, every small box is going to be worth 0.025. So just be very careful. So everything's in volts and amps. No millivolts, no milliamps there. So when you plot, you should get a nice straight line, because obviously that's the line you would expect from a resistor at constant temperature. And then describe how the current through the lamp changes as the voltage applied to it is varied. So as voltage increases, current increases at a decreasing rate. So it wants the lamp there. So if it was that one they was after, as voltage increases, current also increases at a steady rate. Lovely. Oh, and then finally, the group connects two components in parallel with a variable resistor. Variable voltage power supply and an ammeter. Getting tired now. Use the graph and the equation from page 2 to calculate the resistance of the lamp. So I know my, I'm going to get my voltage from the graph. Well, it tells me the voltage, but I'm going to get my current from the graph. And I'll show you how I did that. So when the voltage was 3, the current was 0.85. It's there. Okay. And then to calculate resistance is easy, because just I cover my finger over R, I equals V over I, and there we are, 3 over that is going to give me 3.53 ohms. So that's what the resistance over the lamp is. Okay, the lamp there. That's my resistance. Calculate the ammeter reading at 3 volts. Okay, I messed up first by here. You can see that I was going for something completely different, which they're actually asking me here. This one was more simple than I initially thought, because calculate the ammeter reading. Well, where's the ammeter to? It's at the start before the current splits. Now the current, I know from this, because just looking at my graph, was 0.85. Okay, that was my current. Now I need to know my current for the resistor, and then I need to add them up, because I know that when it comes back around here, they all add up, and then it goes through, and then they'll be the same, and then they'll split. So I'm looking to get really the fixed resistor here, and that was 0.6. So it's going to be 0.6 plus 0.85 gives me 1.45. Okay, and that was for 2 marks. So that was just somewhere I was going. And then I actually went there in the end, because calculate the total resistance of the circuit at 3 volts. So now I'm going to use my total current, which was 1.45, and my voltage was 3, okay, at 3 volts. And that's going to give me 2.07 ohms. Nice little question there for 2 marks. You could have also done it, with this, but that was a long way around, because you would have had to do VIR for each one of these then, and then added them up. So it was a long process. You know, you could have got your resistance for that, and then you could have got your resistance for that, and then added them up, and you would have come up with the same answer. You can try it if you've got time. The last bit of the question there, explain in terms of the current why the whole circuit has less resistance than the resistance of either component. Well, by having 2 loops, what's happening is, you kind of, if you think of it, like I tried to explain in the classroom once, if you got one table and you got 6 students going around that table, and then you got 2 tables, then you offer 2 tables, well, you're going to split that current. You're going to get 3 students going around each table, or you can think of it as doors. Okay, if you've got a class full of kids and there's a fire alarm, and all 20 trying to get out the one door, you're better off having 2 doors, even 3 doors. And the more doors you add, the more pathways for the current. So by having more pathways, by having more loops, you get more current. You get less resistance, because if the current is greater, then there's going to be a smaller resistance. And that's always the relationship with current and resistance. If current is increasing, resistance has to decrease. If resistance is increasing, then current has to decrease. So there's always that relationship. So explain in terms of current why the whole circuit has less resistance than resistance of either component. It's because we've got those pathways. The voltage supply is increased from 0 to 6 volts. Explain how the graph shows that the lamp has a bigger resistance than the resistor at 6 volts. Well, let's grab it. So at 6 volts, which is there, The resistor now has a bigger resistance, has less resistance because there's more current. We just talked about that relationship. See, the filament lamp initially has got, for the amount of voltage you put in, it's got way bigger current, so it's got less resistance, until you get to this point by here, until about 5.5. And you've got that crossover where their resistance is exactly the same. And now the resistor is just going to keep increasing. As the voltage increases, the current's going to keep increasing. But this filament lamp is going to just level off now. And even like if you just put loads of voltage in, it's not going to change its current much. So it's got more resistance at this point. And that's pretty much what that question says. The current through the lamp is smaller than the current through the resistor. So I've even given some values. And that satisfies 2 marks. Use the graph and without calculations, by giving clear reasoning, compare the powers of the lamp and the resistor between 0 and 6. Well, I've said at 5.5, and we just looked at that on the graph, the power is equal since the currents are equal. So at this point by here, the power is equal. But past 5.5, the resistor has a greater current, therefore a greater power value. And that really completes that question. Lovely.